Hi, in this video we will see how to simulate cognitive radio networks in NetSim. Wireless regional area networks (WRANs) operate primarily in low population density areas in order to provide broadband access to data networks. The WRAN systems will use vacant channels in the VHF and UHF bands allocated to the television broadcasting service while avoiding interference to the broadcast incumbents. A typical application can be the coverage of the rural area around a village within a radius of 10 to 30 kilometers from the base station. The MAC can also accommodate user terminals located as far as 100 kilometers with proper scheduling of traffic in the frame when exceptional RF signal propagation conditions are present. To simulate WRAN in NetSim, we navigate to the simulation menu in the menu bar and select New Cognitive Radio Networks, and the simulation environment opens out. The cognitive radio palette on the top has various devices like nodes, switchers, routers, access points, CR base stations, etc., along with other navigation buttons. Now, creating a cognitive radio network is very simple, and all the user needs to do is to click and drop the CR CPEs, customer premise equipment, then base stations and routers, and then link the devices as shown in the video. We proceed to model the applications running on the nodes, or in other words, the traffic on the network. For that, right click on the device and select Properties. As you can see, the node is modeled per the 5-layer TCP/IP stack. Set the application 1 properties as shown. The setting of properties for the application, transport and network layer are available in other videos, and in this video we will focus on cognitive radio properties, which are available in the MAC and PHY layer of the base station. In the data link layer, we can set the DSX request retries. Various timers like the T7 timer is used to calculate the waiting time for the DSA, DSC, DSD response timeouts, while the T8 timer is used to calculate waiting time for the DSA/DSC acknowledgement timeouts, and many more. Next, in the incumbent properties, we can set the operational frequency, start and end values, operational time, operational interval, and more. Finally, in the physical layer, we have channel bandwidth, which is the numerical difference between the upper and lower frequencies of bandwidth of electromagnetic radiation. And then we have modulation, which is the process of varying one waveform into another waveform. In NetSim, QPSK, 16QAM and 64QAM techniques are implemented. Then multiple access via OFDMA, orthogonal frequency division multiple access, cyclic prefix factor, which is used by the PHY in frame transmission in the super frame, IFQP, interframe quiet period length, and more such parameters are available. Once the properties have been set, click the packet trace button and provide a file name. Select the type and its location. Also, do ensure that all the attributes are checked for a better and detailed description. And also enable the event trace. Now that we have created and configured the simulation scenario, we will proceed to simulate it. For that, click the simulation button as shown. Before the simulation is run, select the simulation time, enter the experiment name, enable the packet animation. Finally, the user can also change the seed values for the random number generator if required. Then click the OK button and a command line like window will open and display various messages indicating the simulation progress, and this continues till the simulation is complete. After the simulation is complete, NetSim reports various performance metrics like network metrics, application metrics, link metrics, TCP metrics, cognitive metrics, and more. Now, to see the packet flow animation in the network, click the link View Packet Animation in the left hand side and a window opens showing the network along with playback controls. Let us study the cognitive radio simulation in detail with the help of the animator. First, ARP and IP messages are shared between the routers. Note that in cognitive radio networks there are two control headers, SCH and FCH, and along with we have the US map, DS map, UCD and DCD. The base station sends the superframe control header SCH using the 5-layer and TCP equal to 1 by 4 TFFT to all the CRCPEs after 160 milliseconds. It is transmitted over all data subcarriers encoded by the rate half convolution coder. After 10 milliseconds, the frame control header is transmitted as part of the DS protocol data unit in the DS subframe, and this uses the basic data rate mode. The length of the FCH is 4 bytes and it carries amongst other things the length in bytes for the DS map if it exists or the length of the US map. The FCH is sent in the first two subchannels of the symbol immediately following the preamble symbol. These maps are transmitted using the base data rate mode in the logical subchannel immediately following the FCH logical subchannels. The length of the DS map PDU if present or US map PDU is indicated in the FCH. If the DS map is present, the length of the US map, UCD and DCD are specified in the DS map and follow the DS map in that order. These processes happen every 10 milliseconds. In between, the nodes transmit data packets. Before transmitting packets, nodes send bandwidth request to the base station. In our scenario, CRCPE1 sends the bandwidth request to base station 1. After getting the response from the base station, the node will send the ARP packets for connection establishment between the source and destination. In our case, the destination is CRCPE6, so the packets are sent via the routers. The destination node also sends the bandwidth request to base station 2 and then it replies. Once the connection establishment is complete, CRCPE again sends the bandwidth request to base station 1 and then sends the DSR request to base station 1, and finally CRCPE1 sends the data packet to base station 1. In turn, base station 1 forwards the data packet to CRCPE6 via the intermediate devices and it sends the DSR RSP packet to CRCPE1. This covers the transmission of one data packet in a WRAN network. The entire flow of packet transmission can also be seen via the generated packet trace. And we can see each and every event of the simulation through the event trace. Hope you enjoyed this video on cognitive radio network simulation using NetSim. Thank you.